Hey everyone, hope you're doing great on this beautiful Friday, Saturday, or Sunday. Hopefully, one of those 3 days when you're watching this. So, yesterday in class, we talked about polarity of bonds, polarity of molecules, and how certain shapes, when the elements, like for instance, right here with carbon dioxide, with it having an oxygen over here and oxygen over here, the dipoles cancel out, and it makes the whole molecule nonpolar, although the bonds themselves are polar. And remember, we look at the electronegativity differences to see whether a certain bond is polar, but we look at the overall molecule to see whether that molecule is polar or not. Okay, so we're going to kind of take what we talked about yesterday, and we're going to talk about attractions today. We will review polarity and intermolecular forces a little bit on Monday, but we're going to talk about intermolecular forces today, as well as covalent network bonding. So I promise I'll make this as fast as I can. So we have intramolecular forces and intermolecular forces. Intramolecular forces are covalent bonds, ionic bonds, um, things like that. So those are the stronger types of bonding or forces. They're definitely the stronger versions of them. But we do have intermolecular forces. And intermolecular forces are weaker than both of those types of bonds because they're not within the bond, they are between different molecules, is what you're having here, is what's going on. Intermolecular forces are forces that are between molecules, okay? Not in them themselves, if that makes sense. So these will determine, these intermolecular forces generally determine whether something is a solid, liquid, or a gas at a certain temperature. We know that ionic compounds almost always are solids at room temperature, whereas covalent compounds could be a gas like methane, could be a liquid like water, or it could be a solid like sugar at room temperature, and it depends totally upon its intermolecular forces there. So um, we call these. I'm trying to pronounce this right. This is Dutch, and I'm not very good with that language. But Van der Waals, I think is how it's pronounced. So Van der Waals forces, named after Johannes. That's not right. Van der Waals. So we have different types of Van der Waals forces. We generally call them London dispersion forces because, well, that's what I want to call them. LDFs for short because it's just easier to say. Okay, but there are two types of these forces. There's dipole forces, and then there's dispersion forces, which are the London dispersion forces. Okay, so these are types of intermolecular forces that hold molecules together, essentially, is what's going on here. Okay, so they're responsible for holding molecules together. So there are three types I want to talk about. The first one are dipole interactions. Okay, so they're similar to your interactions with ionic bonds, except they're extremely weak compared to ionic bonds. Ionic bonding is so much stronger than dipole-dipole interactions, but these are within polar molecules. Okay, remember yesterday how we determined whether a molecule is polar or nonpolar? If the molecule is polar, it has dipole-dipole forces, or in other words, dipole interaction. Okay, so that's something you need to know. If it is a polar molecule, and we know that it's polar if it has a lone pair around the central atom, or if it doesn't have a lone pair, but one of these sides is not the same as the other side, so it's not exactly evenly spread throughout, then it's polar. And if it is polar, it always has dipole interactions because you have a net positive end and a net negative end in terms of delta, which is slightly positive and slightly negative. So it's not completely positive, completely negative, but it's slightly positive and slightly negative, as we've talked about. So what's important here to understand is dipole-dipole forces are for polar molecules, okay? So you'll see that here. This could be something like HCl, where the green is the H and the yellow, gold, whatever color there is the Cl. Okay, you have a positive end and a negative end, slightly positive, slightly negative. Should mention that. Not totally positive, not totally negative, but these are interactions that are between molecules, not within the molecule. within the molecule, the bond that holds this molecule together is a covalent bond. But between each molecule, because there's obviously more than one molecule around in a substance, these are the intermolecular forces, and these are dipole forces right here, interactions. Okay, so the positive of one end is attracted to the negative of another end in the same molecule. Well, not the same molecule, but the same type of molecule. So these could all be HCl molecules. So that's the first type. So dipole is for polar molecules. The second type is London dispersion forces, which are the weakest of these interactions by far, but they're just caused by the instantaneous motion of electrons. So at a given moment, something could line up right to give a little attraction, essentially is what's going on here. These are in every covalent compound. So that means they're in nonpolar molecules, and they're also in polar molecules as well. With London dispersion forces, what I'm going to ask that you do, with all these intermolecular forces is, you've had to draw a Lewis structure. Okay, you've drawn a Lewis structure, you've assigned formal charges, you've told the shape, the bond angle, the hybridization by first, I guess, finding the number of atoms the middle is connected to versus the number of lone pairs it has around the middle. We've done all that. Yesterday we looked at whether it was polar or not, and then once you figure out if it's polar or not, you can figure out what types of intermolecular forces it has. Okay, so London dispersion forces are in every molecule. Doesn't matter if it's nonpolar or polar. Okay, so when you are asked questions, like what types of intermolecular forces are in this molecule, you will always write London dispersion forces. They are in every molecule. Okay, so they do, or they're not all created equal, these London dispersion forces, though. Generally speaking, the larger the molecule is, that means it has more electrons. That gives it more opportunities to actually have these forces because you have more electrons and you have really more. It's just the more electrons you have gives you more opportunities for these to interact with one another and create this very weak force between two different molecules. Okay, so something like methane, which is CH4, is nonpolar. Methane only has London dispersion forces. It does not have dipole forces because it's nonpolar. But then something like octane, which is C8H18, well, that's a huge molecule. That only has London dispersion forces as well because it's still nonpolar, but it's much larger, so its London dispersion forces are stronger. Okay, so fluorine and chlorine are gases. Remember, they're F2 and Cl2, Br2 and I2 as well. These are all diatomic molecules, right? F2, Cl2, Br2, I2. Okay, they're all nonpolar, and all they have are London dispersion forces, or LDFs for short. Okay, you can type or you write whatever LDFs, and I'll know what you mean. Okay, but regardless, these two don't have as many electrons as these two, and these two at room temperature are gases. When you get to bromine, bromine is a liquid at room temperature. It has more electrons. Okay, so its London dispersion forces are stronger, its intermolecular forces are stronger, and the only one it has is the London dispersion forces. And what that does is it makes the interactions between these molecules stronger, and then it's harder to break those. So it's harder to you need more energy to put in the molecule for it to break, essentially for it to go from liquid to a gas, solid to liquid, etc., things like that. And iodine has the most electrons, and you know that because it's farther down the periodic table. It has more or a higher atomic number, and because it has more electrons, it is going to be a solid at room temperature. Okay, so that's an example of how when you add number of electrons, it changes up the make of an element. Okay, so looking at these types of intermolecular forces, we have three. Okay, we have that you need to know: London dispersion forces. Okay, the one we just talked about. They are in every molecule, nonpolar and polar. We have dipole forces or dipole interactions. Those are only in polar molecules. So if the molecule is nonpolar, you will not say that it has dipole interactions because it does not. And then we have one more type, and that's a hydrogen bond. Okay, and that is just a stronger type of dipole interaction, essentially. Okay, so a hydrogen bond is a dipole interaction that is between three elements with an H. Okay, so you would need a connection between an H, a hydrogen, hence the name hydrogen bonding, and three elements. Okay, one of them is oxygen. Okay, so if you look at this right here, these are all water molecules. Okay, the red right here, the red one right here is the oxygen, and the white ones are hydrogen. And so a hydrogen bond can form between a hydrogen of one molecule, okay, and the oxygen of another molecule. Do you see that? The oxygens of these molecules are attracted to the hydrogens of the other molecules, okay? Everywhere you see here, there's a red with a dotted line to a red oxygen to a white hydrogen. Okay, there are lone pairs at the top of the oxygen, and that's what they are attracted to, the lone pairs. Okay, so there are three elements that make up a hydrogen bond. Okay, F-O-N, fun, fawn, however you want to pronounce it. That's how, when we had to memorize things, that's what we used to memorize. So only three elements produce hydrogen bonding, F, O, and N. And it's because those three elements are they're really high in electronegativity. Okay, fluorine is 4, nitrogen is 3, and oxygen is 3.5. Those are the three highest in terms of electronegativity. Okay, and so what that does is it creates a special type of bond that is, or intermolecular force that is much stronger than regular dipole-dipole. Okay, so obviously hydrogen bonding always involves hydrogen. Okay, so, and hydrogen bonds are the strongest of the intermolecular forces. So in order of weakest to strongest, it goes London dispersion, then it goes dipole-dipole or dipole interactions, and then it goes hydrogen bonding. And it's important to know that hydrogen bonding is a type of dipole-dipole interaction. It's just a strong, much stronger type of one. Okay. But if you look right here, a hydrogen bond has about 5% of the strength of the average covalent bond. So these intermolecular forces are much, much weaker than the actual bonding that occurs, but they still are important to how the molecule behaves. Okay, which is why hydrogen bonding is the reason why ice would float on water. Okay, that special bonding there. Okay, if water did not have hydrogen bonding, we would be in trouble. Okay, it would not be nearly as polar as water actually is, and a lot of the things that water is used to dissolve, it wouldn't work, right? So we need water to dissolve things. That's how our body processes work. So here is an example that I put on here of hydrogen bonding between molecules. So you don't see the lone pairs here, but they exist. Okay, I would expect you to know that they're here. These lone pairs of this oxygen are attracted to the hydrogen of another molecule. Okay, so that is a connection of a hydrogen bond. All right, the delta positive, delta negative in there. Okay, so those are the three types of intermolecular forces. Okay, we will discuss that on Monday a little bit, and we'll review it as well on Tuesday before we take the test on Wednesday. So the last part of this unit that I'm going to go through really fast is the properties of covalent compounds. We know some, I just mentioned this and we've talked about it in the past, some covalent compounds are liquids and some are solids and some are gases at room temperature. Okay? It is due to their intermolecular attractions. I would know that. That's a very good multiple choice question to put on the test. Their intermolecular attractions affect what state they are in at room temperature. Okay. So that also affects the melting and boiling points. How much energy do you have to put into a molecule for it to melt or for it to boil? Okay. So if you don't have to put too much in, they're going to have very low melting and boiling points. But if you have to put a lot in, it's going to be really high. Right. And one of the strongest types of forces that exist on Earth, bonds that exist on Earth, are the ones between network solids, because it is, even though it is a covalently bonded structure, it's held together by such strong forces. An example of this would be diamond, right? The diamond, is pressurized coal and a couple more things, but pretty much that's what it is. And that's held together by such strong network solids that it would take an insane amount of energy in the form of heat to be able to break those bonds, sometimes even higher than ionic bonding. So diamond is an example of a network solid. Diamond would vaporize to a gas at 3,500 degrees Celsius and above. You're not getting to that temperature. You don't have to worry about that. If we got to that temperature, you would not be worried about your diamonds turning to gas. Okay, so one of the reasons why diamond is so valuable is because unless you just, I mean, it's hard. It's for one, it's hard to break because it's so strong. But two, it's not going to ever melt, ever. Like unless you go to the sun or something like that, or go to the middle of the earth. So here's a table just to look at while you are answering questions on the test or the quiz over the weekend. Here's some properties of ionic and molecular compounds. Most of these I would assume you already know, but it would be good to look at this as well. Okay. Most of this we've actually already talked. I'd say all of this we've talked about before. So just a organized place for it. So, all right. So that's the end of this unit. And so we're ready for a test. I hope you are doing well. Hope everything's going all right this weekend for you. Watch this video. It's an ended puzzle. And also take the quiz this weekend. Let me know if you have any questions. Remember the midterm ends today. Today is Friday. Okay. So I'll have all your grades up